Welcome to lecture 4.4 of Math 1324. We're going to be looking at logarithmic and exponential equations today. Today we're going to talk a little bit about success before we start for our brief pause. And there's kind of 3 points that I like from these quotes. Success is no accident. It is hard work, perseverance, learning, studying, sacrifice, and most of all, love of what you are doing or learning to do. So I like this thought about success and specifically focusing on allowing your interests and passions to drive you, putting first things first, as we saw in the last lecture. It doesn't mean you're going to love everything you're doing, but if you're heading towards something that you are interested in or something that you love, it will make that work much more meaningful to you. I often tell students, many of my students say that they hate math, they can't do math, and yet they want to work in business, etc. And so I share with them to kind of focus on this being a tool in their toolkit that will help them in their jobs, in their career, etc. And that success in math really largely depends upon discipline and focus and practice. And so I remind them that imagine, or I challenge them to imagine that this course, especially students who are worried about being successful, imagine you got a B or an A in this course that you hate and don't think you're good at. What would that say for courses that you are interested in? That that you're capable of really doing anything at that point. So really, the stuff that comes hard to us is we want to put more energy into, more time into. And really, I feel like I'm being very frank here that to be successful in this course, it just keeps taking practice. Practice and discipline to keep doing the work on a regular basis, not doing 6 to 8 hours of math on a Saturday, which makes you hate it more, but doing a little bit every day. That's how you will master it. Just like a sport, you don't show up on Saturday and do all your workouts for the week. Okay? Put your heart, mind, and soul into even your smallest acts. This is the secret of success. This one reminds me of Mother Teresa, who said she never did really big things. What she did was really small things, but she did them really well. And again, I think this is also talking to you. It may not be your favorite part of the job or the favorite, it may not even feel connected to some degree, but putting your heart and soul into those things and doing well really will pay off in the long run. And then the last one, I think that a lot of people overlook, especially in the American culture, quitting is bad, failure is bad, and that's kind of bullshit. Everyone quits, and there is a time to quit. Sometimes, there's another quote, I should have put it in here, that says, courage does not always roar. Sometimes it's the quiet, still voice at the end of the day that says, I will try again tomorrow. And sometimes it makes sense to quit and to start over at a different time. And you will fail throughout your career. I'm still making failures. And failure is not the opposite of success. It's part of success. The key is to learn from mistakes, to own them quickly, to fix them. And you'll earn much more credibility and respect from your peers. And you'll continue to learn and not be ashamed of mistakes, or you'll have a much more humble attitude for your own mistakes and others. You'll be much more gracious. Students often apologize to me when they're doing poorly or have failed a course, and I openly share that I have no judgment about it. In fact, my judgment is more like, maybe this is your time to fail, and I'll support you fully in your failure. Because I know in my own life that failure often has been the best lessons. There's been something really good, some change I needed to make that came from failing and forcing me to stop and look at what was going on. And the other side of it is, as your teacher, there are a million reasons why you could have failed. And so I can't have any judgment about that. Maybe you were lazy. Maybe you didn't do the work. But also, maybe you had to have 2 jobs for your family. Maybe you had some serious personal issues, lost a spouse, lost a family member. So for me to judge failure, it would be so irrelevant and inaccurate. All right, so let's get into the lecture. First, we're going to look at logarithm equations. Remember, an equation is when you have an equal sign. When an equation involves only logarithmic terms, use the logarithm properties to write each side as a single logarithm. Then use the following fact. Let u, v, and a be positive real numbers with a not equal to 1. If the log base a of u equals the log base a of v, then u equals v. Well, this kind of makes sense, right? Because we have the log of log of u equals the log of v, and the only way that these two are going to be, since they have the same base, the only way that these two are going to be equal in this original equation is if the arguments are equal, u equals v. Okay, again, these are for equations that involve only logarithmic terms. So look at this example. Log minus log equals log plus log. So we have a whole, every single term, everything that we're adding or subtracting here, it has a log in it, is a log. Okay, that's when we're going to use this method. Okay, so when every term is a log, we write both sides as a single log, drop the logs, setting the arguments equal, and solve. Okay. Notice on the left here we have subtraction, and so we can use the quotient property that we learned in the previous section to rewrite these as the log of the numerator over the log over the denominator. Remember, anything positive is the numerator, anything negative is the denominator. This is the quotient power on the left. On the right, we have addition. This is the product power. The sum of two logs is equal to the log of their product. Okay. So when we're talking about rewriting both sides as a single log, we're talking about using the quotient and product properties that we learned in the previous section. Now, since we have log equals log, just like the setup here, we can drop the logs. That's a little joke there, huh? It's time for you to drop a log in math. Haha. And set the arguments, which are in yellow here, equal. So we get 48 over x equals, well, 6 times 1/2 is 3, so I just did that math there. And now we just simply solve for this. This is algebra now. Multiply both sides by x. It disappears on the left, and we get 48 equals 3x. Divide both sides by 3, and we get x equals 16. Okay? So again, this is the process you'll use when every term has a log. So you'll look at the original equation, log minus log equals log plus log. If it's all logs, simply rewrite each side as a single log using the properties of logarithms. Then drop the log, setting the arguments equal, and solve using algebra. So let's do another one. Again, here we can see we have log equals log minus log. So we're going to rewrite each side as a single log. On the left, we already have a single log. On the right, again, we have a quotient because it's a difference. The numerator is the positive part, the denominator is the negative part, so we have the log of x plus 3 over x minus 1. We can now drop the logs and solve this. Now this gets a little more complicated. Remember, when we're solving rational expressions in algebra, we multiply both sides by a common denominator, so we're going to multiply both sides by x minus 1. It cancels out on the right, and we have x times x minus 1 on the left. We then do the distribution. We get x squared minus x on the left equals x plus 3. I can see here that I have a quadratic equation, so I'm going to set this equation equal to 0. So I'm going to subtract the x from the left from both sides, and I'm going to subtract the 3. And so I get x squared minus 2x minus 3 equals 0. And now we can either use the quadratic formula or we can factor. Factoring is pretty easy here. This is the factors are x minus 3 and x plus 1 equals 0. I then set each of the factors equal to 0 and solve. X minus 3 equals 0, which gives me x equals 3. X plus 1 equals 0, which gives me x equals negative 1. Now, with these logarithm equations, remember that logs have a rule that you cannot take the log of a negative number. So I have to plug these back in and see if the arguments are negative. So when x equals 3, I get 3 plus 3, which is positive 6. That's okay. And 3 minus 1, which is positive 2, which is okay. When I have negative 1 here, I get negative 1 plus 3, which is positive 2. That's okay. Negative 1 minus 1 is negative 2. That doesn't work. So this answer here, x equals negative 1, will not work. So you must check the answers and make sure that none of your x values give you a negative value. Okay? It doesn't mean that x cannot equal a negative number. It means that any of these arguments cannot be negative. And so in this case, x can't be negative because on the left side we just have the log of x. I didn't pay attention to that. But let's say this was just log of x plus something. And this was x minus 3. So we could have values in here like positive 1 and positive 2 that would work or wouldn't work because it would make it. So when you're checking, you're seeing that when you plug it into the argument of the log, you don't get a negative answer because you cannot take the log of a negative number. So here's a couple more. I'm going to walk through these pretty quickly. These are just more examples for you to see how it's done. Number 1, we already have a single log on both sides, so all we have to do is set the arguments equal. Log equals log, so we just drop the logs because step 1 is already done, and set the arguments equal. X plus 3 equals 2x minus 5. We get all the x's on one side, all the constants on another, and when we solve this, we get x equals 8. In number 2, we have a quotient property on the left side. So we have the numerator is positive over the denominator, which is negative. And then we just have the log of a quotient. Don't get confused here. This is just the log of a constant here, so of a fraction. It's not a quotient rule on the right. So I can rewrite the left side as a single log, which I've done there. Then I drop the logs, and I get 8 minus k over 3 plus 4k. Equals 9 over 11. Here I'm going to cross multiply to solve this to get rid of the fractions. When I have fraction equals fraction, the easiest thing to do is to cross multiply. So I get 11 times 8k is 88k minus 11 times 7, which is minus 77. 9 times 3 is 27, and 9 times 4k is 36k. And then I get all the variables on one side. I get 52k, all the constants on the other equals 104, and k equals 2. I plug these back in to check, and I can see that this only gives me positive values. For number 3, again, we have the quotient rule on the left. So we have 3x plus 1 over 5 plus x equals 2. Again, I'm going to cross multiply using 2 over 1. And so I get 3x plus 1 equals 10 plus 2x. Again, I get all the x's on one side, I get all the constants on the other, and this is a really easy one to solve. Number 5 is a little bit more involved. Because we have a multiplier in front, so we're going to have to change this using the power rule first. Okay? Remember, when I multiply a log by a constant, that multiplier is the same as having an exponent on the argument. So this, on the left side, we can rewrite number 5 as the log of the quantity of x minus 3 squared. On the right, we have a product rule. Remember, the sum of two logs is equal to the product of the log of their product. So this is the log of 4 times x plus 5. Okay? So once I drop the logs, then I get x minus 3 squared. Again, we moved the 2 as the power using the power rule, and then the product 4x plus 5. Again, if we square this out and distribute the 4, we can see we have a quadratic equation. Set it equal to 0. Factor it. Set each factor equal to 0 and solve. I'm not going to go through these algebraic steps. You can go through these and make sure you understand. And then I check both of these. I plug these back in. into the original. Negative 1 minus 3 would give me a negative 4. 11 minus 3 gives me 8. That's okay. Negative 1 plus 5 is positive, so that's okay. But the negative 1 doesn't work in the first argument. Negative 1 minus 3 is negative 4, and we cannot take the log of a negative number. Okay? So that's a number of examples that should help you get through the homework. There are some more complicated and confusing ones there. Sometimes we have logarithmic equations that are made up of terms that are not all logs. For example, down here in yellow, you see the log minus a log equals a constant. This could also be log minus log equals 2x, some kind of expression here. But notice the 2 does not have a log in it. And that's what this type of equation, when not all the terms are logs. And we're going to use a different strategy to solve these. We're first going to get all logs on one side. Then on that side, we're going to rewrite them as a single log. We're then going to convert that logarithm into an exponential. And then we're going to solve. So let's see about doing that. Get all logs on one side. Already done. Rewrite as a single log. Well, here I have subtraction, so this is the quotient property. So I have the log of 2x over 3 on the left side. Okay. So I have all the logs on the same side. I've rewritten it as a single log. Now I want to convert this logarithm to an exponential. Do you remember how to do that from section 1? What's my base? 4. What's my exponent? My base is 4, my exponent is 2, and my answer is 2x over 3. So I get 4 to the power of 2 equals 2x over 3. Base, exponent, answer. Now I'm going to multiply both sides by 3 to get rid of the fraction. And I get 48 equals 2x. I'm going to divide by 2 to solve, and I get x equals 24, which I can see is going to be positive, so I have no problems. Let's try another. The log equals a constant. Again, I don't have all log terms because there's no log with the 3 on the right. I'm going to get all logs on one side. Done. Rewrite as a single log. There's only one log. Done. Then I'm going to convert this to an exponential. So this one has a lot of it done already. But I don't see a base here. Do you remember what the base is when there's not a base written at the bottom of the log? This is called a common log with a base of 10. So I have 10 to the power of 3, which is the exponent, equals the answer, 5x plus 10. This is a very simple algebraic equation. 1000 equals 5x plus 10. Subtract 10, divide by 5, and I get 198. Plug that in. I can see it's still positive, and so I'm in good shape. Let's try another one. The log of 16 equals 2 plus the log of 2x. Again, I have log equals constant plus log. Again, the 2 does not have any log with it, so I have to use this other method to solve. I want to first get all logs on one side. Since I'm adding 2x on the right side and I want all the logs on the same side, I'm going to subtract the log of 2x from both sides. And this gives me the log of 1600 minus the log of 2x equals 2. I now want to rewrite as a single log on the left side. Since it's subtraction, I know this is a quotient with the positive log being the numerator, the negative log being in the denominator. So I get the log of 1600 over 2x equals 2. I am now going to rewrite this as an exponential. Again, I have a common log here, so that's a base 10. So I get 10 to the power of 2 equals 1600 over 2x. If I cross multiply, I get 200x equals 1600. Divide by 200 and I get x equals 8. And I can see that's only giving me positives, so we're good to go. All right. Let's look at a few more of these. I'm going to work through these pretty quickly. You can pause it and try them. I actually suggest that you do try it and then hit play and see if you got the answer right. So I just have a single log here, so I can immediately go to step 3, which is to rewrite as an exponential. 3 to the power of 2 equals 6x minus 2, and then I can solve this. I'm not going to go through those algebraic steps. That one's pretty easy. Number 9, I have a quotient. All the logs are on the same side. So I have and it's a subtraction or a difference, so I have a quotient with the log of x over x plus 4 equals -1. Again, here my base is 10 because it's the common log, so 10 to the power of -1 equals x over x plus 4. It's a good idea to rewrite that 10 to the -1 as a fraction. Remember that a negative exponent means it goes to the other side of the fraction, in this case in the denominator. And then I can cross multiply. 10x equals x plus 4. And I get x equals 4/9, and I can see when plugging that in that those are all positive values. In number 12, I have logs on both sides. The first thing I want to do is to add the log of x plus 8 to both sides so that all logs are on one side. Now I want to make it into a single log. I see I have addition, so this is a product. So I have the log of x minus 4 times x plus 8 equals 3. Now I've handled 1, 2. I need to rewrite this as an exponent. My base is 4, my exponent is 3, and my answer is x minus 4 times x plus 8, which if I multiply or FOIL that out, I get x squared plus 4x minus 32 equals 4 to the 3, which is 64. I see I have a quadratic, so I'm going to set it equal to 0 by subtracting 64 from both sides. I'm then going to factor it. I get x plus 12 times x minus 8. Setting each factor equal to 0, I get x equals -12 or x equals 8. I plug those in and I see that x cannot equal -12 because that gives me an answer. So that's not a valid answer, and the only answer that's possible is x equals 8. Oops. This is actually number 13, not 12. I have the log of x plus 9 minus the log of x equals 1. They're both on the same side. Using the quotient rule, I get the log of the positive term as the numerator over the negative as the denominator equals the natural log of x plus 9 over x equals 1. I now rewrite this as an exponential. What is my base? E. Remember Euler's constant? So this is e to the power of 1 equals x plus 9 over x. E to the power of 1 equals x plus 9 over x. Rewriting as an exponential. I cross multiply and I get x e to the 1, or xe, x times e equals x plus 9. Okay? So a lot of students don't know what to do here. Remember, just follow the rules. Get all the x's on one side, get all the numbers on the other. So I get x times e minus x equals 9. Students still get a little stuck here, not sure how do I solve this when there's two terms with x in it. Factor out the x. Factor out an x on the right side. Notice now I have 9 equals x times e minus 1. Now I can divide both sides of the equation by this e minus 1. And so I get x equals 9 divided by e minus 1. Plug this in your calculator and you get an answer. Sometimes you can leave the answer in this form, but here you can, it might tell you like to find the approximate answer to the thousandth place or 3 decimal places. This is an important problem to understand, especially when we get down to this line 4. Students get stuck here sometimes when they see that there's an x in each term and they can't figure out how to solve just for x. You're going to factor it out and then divide by that other piece. Now we're going to look at exponential equations with the same base. An equation in which all the variables our exponents is called an exponential equation. When such an equation can be written as two powers of the same base, it can be solved by using the fact, let a equal a positive real number with a not equal to 1. If a to the power of u equals a to the power of v, then u must equal v. If we have the same base set up as equal, if we have two exponents that are equal and they have the same base, then the exponents must be equal, and that's what this is saying. Okay? When this is the case, so you're going to check to see if both sides can be written in exponential form with the same base. Here it doesn't look like it in neither of these problems that these are the same base exponent. In fact, on the right side here, 16 is not even an exponent, and 27 is an exponent. But 16 can be written as a base 2 exponent. What about 9 to the x equals 27? Well, let's hold on that for a minute and go back to the process. So the first thing we're going to do is to rewrite both sides of the equation as the same base exponent. So here we have 2 to the power of x plus 2 equals 16. Well, 16 is equal to 2 to the power of 4. So I can rewrite 16 as 2 to the 4th power. Notice now I have the same base exponential. I have this setup that we just talked about. Now here comes the joke again. I got lots of jokes for these exponential and log. With these exponentials, you're going to become a DJ. Drop the base, and set the exponents equal. If I drop the base here, I get simply x plus 2, the exponent equals 4. Simple thing to solve, x equals 2. Now, again, going through those steps, we're going to rewrite both sides as the same base exponent. We're going to drop the base, setting the exponents equal, and then we're just going to solve using algebra. So this one in the blue is a little bit confusing. 9 to the power of x equals 27. Well, 27 is not 9 to a power. It's 9 times 3. That doesn't work. But it is 3 to the power of 3. And 9 is 3 squared. So in this case, I have to rewrite both sides of the equation as a base 3 exponential. Well, 9 is 3 squared, and 27 is 3 cubed. So I have 3 squared raised to a power of x. When I raise a power to a power, I multiply the exponent. So I get 3 to the power of 2x equals 3. Now I have this simplified with the same base exponents. Just like our setup, I can drop the base. I can be the DJ and drop the base. Setting the exponents equal, I get x equals 3/2. Let's look at some more of these again. Again, I'm going to walk through them pretty quickly. In number 23, we have a base 2 problem, 2 to the power of x minus 1. Let me go ahead and get my pointer here again. 2 to the power of x minus 1 equals 8. Well, 8 is 2 to the power of 3. I now have that set up. I can drop the base, setting x minus 1 equals 3. Add 1 to both sides, and I get x equals 4. Number 25, I have 25 to the power of negative 3x over 3125. I would first check to see if 25 times 25 times 25 gets this, and I can just use my calculator. It doesn't, by the way, but I do know if I try 5s that this is 5 to a power, and 25 is 5 squared. So I can rewrite both sides as a base 5. 25 is 5 squared. You can see that again with the power on the outside of the exponent, of the parenthesis. And on the right, 3125 is equal to 5 times to the power of 5. 5 times 5 times 5 times 5 times 5. Again, when I raise a power to a power, I multiply the exponents. So I get 5 to the negative 6x equals 5 to the 5th. Drop the base, setting the exponents equal, and solving. Our last one is a little bit even more complicated. But remember that 1 over 16, well, 16 is 2 to the 4th. We saw that in a previous problem. Well, remember that I can use negative exponents to move that into the numerator and set this up as a same base equation for exponentials. Okay, so pay attention to number 30 when you have fractions in there, and remember to use negative exponents so you can set them equal. So I get 2 to the power of x squared minus 4x equals 2 to the negative 4. I now drop the base, setting the exponents equal. I see I have a quadratic, so I set it equal to 0. I then factor it, and I get x minus 2 squared, and so x equals 2. Okay, so again, when I'm looking at these problems and they have the same base, or I can rewrite them as the same base, and I might have to use my calculator to figure that out. Once I have them rewritten as the same base exponent, then I can drop the base and set the exponents equal and solve algebraically. Our last type of equation is when we have exponential equations involving different bases. These can often be solved by using the power property of logarithm, which is repeated here for natural logarithms. If u and r are real numbers with u positive, then the log of u to the power of r equals r log u. This was the power property where we were able, if the argument has an exponent on the entire argument, we can bring that down in front as a multiplier. And this will help us solve these equations. You can see here I have a base 3 and on the right a base 5. There's no way I can rewrite both of these the same way. Okay, here I have a base 3 and a base 4. They are not a common base problem. I can't try to figure out, like, multiply this by 4 and this by 3. That doesn't work when I have exponents, because you can't just multiply 4 times 3 when there's an exponent on it, because the exponent, remember, comes first in order of operations. So this isn't about finding a common denominator or a common multiple. You've got to, when they are different bases, you've got to use a different process. And what we're going to do is when we have a different base equation, we're going to take the log of both sides of the equation. If there are any e terms, if this was 3e to the x, we would want to use natural log. Whenever you have an e or Euler's constant in an equation, you want to use the natural log. Okay, so we're going to take the log of both sides of the equation. Okay, remember that log equals log. We saw that rule before. Then we're going to use the power rule to drop the exponent down in front as a multiplier. And then we're going to solve this. We're going to simplify it to solve for x, and then we're going to use our calculator to find the value. Okay, so the first thing we want to do is take the log of both sides. So we get the log here, and we can take either one. In this case, there isn't an Euler's constant, but we can still use the natural log. It doesn't matter which one we use, but if Euler's constant is there, you definitely want to use the natural log. So I have the natural log of 3 to the power of x equals the natural log of 5. I can now use the power rule to bring the exponent x down in front. And so I get x log 3 equals 5. Well, I want to solve for x, so I divide both sides of the equation by the natural log of 3, right? This is x times the natural log of 3 equals the natural log of 5. So I divide both sides of the equation by the natural log of 3. This is now simplified, but I want to know what the value is, so I'm going to plug this into my calculator, and I'm going to get 1.465. Let's try another problem. Here again, I see I have two different bases. This is much more complicated, so pay attention to this problem. I'm going to take the log of both sides. Now my exponents are more complicated, so it's going to make my problem more complicated. I'm going to bring this exponent down in front, 2x minus 1 times the natural log of 3. And I'm going to bring this exponent down in front, x plus 2 times the natural log of 4. It's very important that I put these in parentheses so that I don't just think this is 2x minus the log of 3. Okay, this is distribution, and that's where this gets complicated. So it's 2x log of 3 minus log of 3 equals x log of 4 plus 2 log of 4. I've just done the distribution, multiplying log of 4 times x and times plus 2, log of 3 times 2x, and log of 3 times negative 1. Now don't get freaked out here. Anything that has an x, we're going to put on one side. Anything that doesn't have an x, we're going to put on the other. That's how we solve all algebraic problems. So we're just going to do the same thing. So I'm going to subtract x log 4 from both sides to move it to the left. I'm going to add log 3 to both sides to move it to the right. So I get 2x log 3 minus x log 4 equals 2 log 4 plus log 3. Again, students get stuck here. They don't know what to do. Yeah, I have x on the left, but there's a couple terms. Remember what we said before, factor out the x. If I factor out an x from the left side, I get x times 2 log 3 minus log 4. Right? If I factor out an x here, I now have the x totally isolated, and I can divide by this term in here, this expression here, 2 log 3 minus log 4. So I'm going to divide both sides of the equation by this 2 log 3 minus log 4, and I get this setup. This is tough to do in your calculator, so practice it. Okay? It's tough to get the right answer because of order of operations. It's very important when you have this kind of setup that you put the entire numerator in parentheses, 2 log 4 plus log 3, parenthesis, divided by, put the entire denominator in parentheses, 2 log 3 minus log 4, parenthesis, and then hit enter. Let's do a quick problem here. And this will be our last slide, and it's been a little bit long lecture. The number of total subscribers in millions to Netflix can be approximated by the function g of x equals 9.78 times 1.07 raised to the power of x, where x equals 1 corresponds to the first quarter of the year 2009, x equals 2 corresponds to the second quarter of 2009, etc. Assume the model remains accurate and determine when the number of subscribers reach 28 million. This is data from the Wall Street Journal and the Associated Press. So what are we looking for? We're trying to find when. So we're going to need to know the x value. We're trying to solve for x because that tells us when by quarter. The subscribers reach 28 million. Well, the subscribers is what our function is. This is the g of x. So we know that g of x equals 28 million. Okay, so we can set up an equation. We know what g of x formula is, and we know what the answer is. So we get 9.78 times 1.07 to the power of x equals 28. Okay. Well, we cannot, first of all, we have a multiplier here. And so the first thing I'm going to do is divide both sides by the 9.78. to see if I can find a common base. I don't have the common base. There's no way that 1.07 is going to be the same. I can rewrite this left side, and I could have written this as I could have done the math here with my calculator and got a decimal, but it's really kind of better to not do that because we're probably going to have to round, and I don't want to round until the very end if at all possible when solving problems. Since I have a different base problem, I'm going to take the log of both sides. I am then going to use the power property to bring the exponent down in front. So I get x log 1.07 equals the natural log of 28 divided by 9.78. And now I'm just going to simply divide by the natural log of 1.07 on both sides. Again, this is a little bit complicated problem to put into your calculator, especially in the numerator because I have multiple parentheses. I have a parenthesis around the whole numerator, and then I have a parenthesis around the argument as well, 28 divided by 9.78, divided by parenthesis log 1.07. Okay, try that in your calculator and see if you get 15.5. Now the answer to this problem is not 15.5, and this is another great lesson for a test, okay? Because we're trying to find when the number reached 28 million, and 15.5 does not give that to us, okay? So this is 15.5 quarters later, okay? Well, there's 4 quarters in a year, so we're almost 4 years later. We're not quite 4 years later, right? We're 3 and some time later. So the 15th quarter corresponds to the 3rd quarter of the year 2012. 3 years later would be 2012, right? We're not quite at 4. Do not round this to give yourself 2013. 15.5 means we're still in the year 2012. And in the between 15.5 and 16, we're in the last quarter. So this is the third quarter of the year 2012. So you kind of have to be able to interpret the data using some logic and slowing down and not jumping to intuitive pieces. All right, well, that's the end of the lecture. Reach out if you need any help.